The second section in the Growth Models chapter deals with exponential models. And again, as we mentioned in the first section with linear models are okay in the short term, but in the long term, they usually fail to make good predictions about real-world situations. So exponential models get a little closer to the truth, and they're a little more powerful at making predictions. So we'll illustrate this with a population growth problem. Say we're tracking the population of fish in a lake, and every year 10% of the fish have surviving offspring. So of course this is still a simplified model, but it'll get us to introduce exponential models. Now, unlike linear growth, we're not adding a constant amount each time period. Instead, we're adding a percentage of the current population. So here's what the recursive model looks like. We have the initial population is 1,000, and then each population is the population of the previous time period plus 10% of that. So again, the growth is not a constant amount, but rather is a percentage of the population. So of course, as the population grows, the amount that this grows by will also increase. So if we follow this out and derive this explicit or closed form model, we get that the population is the initial population times 1.1 raised to the power of t. And that's why it's called an exponential model, because there's this exponent happening. And specifically it's called exponential because the variable, the t, is in the exponent, as opposed to being in the base. And if we look at this table, remember from the linear models, the growth from the previous year was constant as we go. With an exponential model, the growth isn't constant, but rather the growth rate depends on the population at any given point. So there's a constant percentage growth, but not a constant numerical growth. But notice if we start graphing this, if we just graph a few terms, this is hard to distinguish from linear growth. It looks like this could be tracked by a line. And that's the reason that we talk about linear models being okay in the short term, because in the short term, an exponential model doesn't look that different from a linear model. But if we plot more terms, that deviates dramatically from a linear model. If we followed this line straight out, it wouldn't be a very good prediction of what's actually happening. This exponential model deviates from the linear model. So we summarize this exponential model here, and this is one of two exponential models that we'll see in this section. The other one will involve the number e in the exponential model, but we'll see that in a minute. So if we've got this growth rate that depends on the population at any given point in time, that's our exponential model. And the growth rate is r, and then we define a growth multiplier. We also make a note here that we can talk about exponential decay the same way, and all that means is that the growth rate, quote unquote, is negative. So it's essentially a decay rate in that case. So the model stays the same, but the growth rate is negative if it's an exponential decay problem. And then we do a few examples with this where we fill in this model, and just like we did with the linear model, the two pieces we're interested in are, if we're given a point in time, can we find the population? And then if we're given a population, can we find that point in time? Now for the second part, we need an extra tool, which we'll talk about a little bit later, logarithms, but we'll get to that later in this section. So for now, we just plug in the given point in time and predict the population. Another example here where we're given data rather than a growth rate, but we can use these points to calculate the growth rate. And to do that, we have to solve this algebraic problem, but the details are shown in this example. So we can find a growth rate if we're given a few data points, at least two, to find r. There's a little more detail here about finding these roots that you need for that problem, and then a little blurb about whether the data is linear or exponential, just making sense of when you look at a model, should you use a linear model or an exponential model. Then we get to exponential growth with this special number e, and we define it here, and this is also defined in the financial math chapter. when we talk about compound interest. But it turns out that exponential growth is really just compound interest, and linear growth is simple interest, or rather, simple interest is an example of a linear growth model. In any case, we have this number here, and this we won't go into too much detail, but this is a special number for lots of reasons. But also, any exponential model can be written with this number as the base. Here we're given a model that has that, and we're asked to make the same kind of predictions we did before. But in general, any exponential model can be translated into that, although we won't show the details of how to do that. And then, of course, we mentioned radioactive decay as well. Nothing special, it's just, again, the growth rate is negative. But summarizing the exponential growth and decay, as I said, we have two exponential models, the one we showed earlier, and then the one here, with e as the base. And so we still have a growth rate, but we're calling it k because it's a different number than it was in the original, or in the previous model. But it's still an exponential model. And the reason it's exponential is that the variable, the t, is in the exponent. And we do some examples with that, with radioactive decay. Finally, we get to using logarithms to solve for time. So again, we said we either want to take a given point in time and predict the population, or find the point in time that the population reaches the given point. So if we want to solve for that, it gets a little trickier than earlier examples. The linear ones were easier to solve for t. Exponential ones are a little trickier, and we have to use logarithms. So I won't go into too much detail, but essentially what we do in this subsection is talk about what a logarithm is. We define it, we go into some rules, and then we get some practice evaluating logarithms, both by hand and with a calculator, and then solving equations with logarithms, which is really what we want to get to. And that's what helps us do this problem of solving for time when we're given a specific population that we want to reach. And we do an example with that, predicting the population, or the point in time that the population hits a certain amount. The last thing in this section is sort of a side note, just an application of exponential models, and that's Newton's law of cooling. So this is a heat transfer problem where if we leave something out, let's say for instance a hot cup of coffee out, you expect it to cool down until it reaches the temperature of the surrounding environment, or the medium is the word we use for that. Similarly, if you put out like an ice cube, you'd expect that to warm up to the temperature of the medium, or the environment. And without going into too much detail, this is what the model looks like. The temperature at any point in time looks like the temperature of the medium plus the initial temperature of the object minus the temperature of the medium times e to the kt. And k is this growth rate, or heat transfer rate, which depends on the whatever the situation is. So maybe the coffee cup is insulated, maybe it isn't, maybe there's a fan blowing on it that changes the convective heat transfer, and all sorts of things. But basically, by taking a couple of data points, we can figure out what that k is and then make predictions with this model. So we go through an example here where we have a coffee cup that starts at a certain temperature, and we're given the temperature of the medium, and then we can go through and solve for k with the two pieces of information we have, the initial temperature and then the temperature after 10 minutes. So we go through and we solve for k, and that tells us our full model. Once we know that, we can plug all the pieces in and get this model. And then we can predict forward in time what the temperature will be at any given point. And then also we can predict when it will reach a certain temperature. So we plug in that and solve for t using logarithms, like we showed earlier. So we can make predictions about what its temperature will be at any given point and when it will reach any given temperature. And also we can graph its temperature, and we notice that it cools rapidly at the beginning, but then as it reaches the temperature of the medium, it starts to slow down and level off, which makes sense. It's not going to cool down to get colder than the environment. It's going to all settle out and reach what we call steady state, or equilibrium, where the coffee cup cools down until it hits the temperature of the medium, or the surrounding environment. So that's just an application of exponential models.